Imagine that tomorrow morning, every scientist on Earth wakes up to a shocking discovery. Not that a new planet has been found, not that aliens have been detected, not even that a new force of nature exists. Instead, they discover something far stranger. They discover that space itself could have had a completely different number of dimensions. The room around you seems ordinary. You can move left and right, forward and backward, up and down. 3 directions. 3 dimensions. It feels so natural that most of us never question it. But here's the mystery. Why 3? Why not 2? Why not 4? Why not 10? Why does the universe permit exactly 3 large dimensions of space? This question sounds deceptively simple. In reality, it touches some of the deepest mysteries in physics, cosmology, mathematics, and the nature of existence itself. Because if space had even 1 extra dimension, or 1 fewer dimension, you probably wouldn't exist. Neither would stars, neither would galaxies, neither would chemistry. The entire cosmic story might collapse before it ever began. And yet modern physics offers no final answer. The universe simply presents us with 3 dimensions and refuses to explain why. Today, we are going to follow this mystery, from the scale of your own body all the way to the largest structures in the cosmos. We will travel through the mathematics of geometry, through the work of Newton and Einstein, through black holes and quantum mechanics, through hidden dimensions predicted by modern theories, through galaxies, cosmic evolution, and the possibility that reality itself may be far stranger than it appears. By the end, we'll arrive at a place where physics meets philosophy, a place where scientists are still searching for answers, and where one of the biggest questions in science remains unresolved. Why does space have 3 dimensions? To appreciate the mystery, we first need to understand what a dimension actually is. The word is used constantly in science fiction. Movies talk about parallel dimensions, books describe higher dimensions, physicists discuss extra dimensions hidden from view. But in physics, a dimension has a much simpler meaning. A dimension is simply an independent direction in which movement is possible. Imagine a tiny creature living on a perfectly straight line. It can move only in 2 directions, forward, backward. Its entire universe consists of 1 dimension. Now imagine a creature living on a flat sheet of paper. It can move left and right, forward and backward. This world has 2 dimensions. Every possible location can be described using only 2 numbers. Add another independent direction, up and down, and you obtain our familiar 3-dimensional world. Every position around you can be described using 3 coordinates: length, width, height. Nothing seems unusual about this. Yet, from a mathematical perspective, there is no obvious reason reality had to stop at 3. Mathematics allows 4-dimensional spaces, 5-dimensional spaces, 100-dimensional spaces, even infinitely dimensional spaces. Mathematicians routinely work with such spaces. The equations don't complain. The logic remains perfectly consistent. So why does physical reality seem different? Why does the universe choose only 3 dimensions for everyday space? To understand why this question became important, we need to go back several centuries. For most of human history, nobody seriously questioned the dimensionality of space. 3-dimensional space appeared obvious. It seemed like a basic fact of existence. Then science began uncovering laws that appeared astonishingly precise. One of the most important came from Isaac Newton. Newton's law of gravitation revealed that every object attracts every other object. The force weakens with distance according to a specific mathematical rule. Double the distance, the gravitational force becomes 4 times weaker. Triple the distance, the force becomes 9 times weaker. This relationship is called the inverse square law. At first glance, this seems like an arbitrary feature of gravity. But later physicists realized something remarkable. The inverse square law emerges naturally from three-dimensional space. Imagine placing a lamp at the center of a sphere. The light spreads outward in every direction. As the sphere grows larger, the same amount of light must cover a larger area. In 3 dimensions, the surface area of a sphere grows according to the square of its radius. As a result, the light becomes weaker following an inverse square pattern. Gravity behaves similarly. Its strength spreads through 3-dimensional space. And because space has 3 dimensions, gravity naturally follows the inverse square law. This insight led scientists to a fascinating realization. The laws of physics are deeply connected to the number of dimensions. Change the dimensions, change the laws.
Change the universe. Suddenly, dimensionality was no longer a trivial detail. It became one of the most important ingredients in cosmic architecture. The universe is not merely happening inside 3-dimensional space. The universe is shaped by 3-dimensional space. Every star, every planet, every galaxy, every atom, every living organism all depend on the geometric framework in which physical laws operate. To see how profound this is, imagine a universe with only 2 dimensions. At first, it sounds harmless. A flat universe, like an endless sheet of paper. Creatures could still exist. Perhaps they could walk around. Perhaps they could build civilizations. But very quickly, strange problems appear. A 2-dimensional digestive system would divide a body into separate regions. Food passing through an internal tube would effectively cut the creature into disconnected parts. Blood circulation becomes problematic. Complex anatomy becomes difficult. Even simple biological structures become dramatically constrained. Physicists and biologists have explored such possibilities and discovered that life becomes far harder to organize in lower-dimensional worlds. But biology is only the beginning. The deeper problem involves gravity itself. In a 2-dimensional universe, gravity would not follow the inverse square law. The geometry changes, the spreading of gravitational influence changes. Planetary orbits become unstable. The elegant celestial mechanics that govern our solar system disappear. Stars may struggle to form. Long-term cosmic structures become difficult to maintain. The universe begins losing many of the features we take for granted. Now consider the opposite direction. Suppose space possessed 4 large dimensions instead of 3. At first, this seems like an upgrade. More dimensions, more possibilities, more room for complexity. Yet physics reveals an unexpected consequence. Gravity would weaken much faster with distance.
In 4 spatial dimensions, gravitational attraction follows an inverse cube relationship rather than an inverse square relationship. This subtle mathematical change creates enormous consequences. Stable planetary orbits become nearly impossible. Planets either spiral into stars or escape into deep space. The delicate balance that allows Earth to circle the Sun for billions of years would vanish. The same problem appears inside atoms. Electrons occupy stable quantum states, partly because of how forces behave in 3 dimensions. Alter the dimensionality, and atomic structure itself may collapse. Matter as we know it might never exist. No chemistry, no molecules, no DNA, no observers asking questions. This observation fascinated physicists throughout the 20th century. The universe appears strangely optimized for complexity. 3 dimensions are not merely sufficient, they may be uniquely favorable. A famous argument emerged from this realization. If intelligent observers can only arise in universes with certain dimensional properties, then perhaps it is no surprise we find ourselves in such a universe. This idea later became associated with the anthropic principle. The principle does not explain why the universe has 3 dimensions. If countless universes exist with different dimensional structures, intelligent beings would naturally find themselves in one of the rare universes capable of supporting complexity. Whether this is an explanation or merely a restatement of the problem remains controversial. Many physicists remain dissatisfied. After all, saying we observe 3 dimensions because otherwise we wouldn't be here feels incomplete. It describes a selection effect. It does not reveal the deeper mechanism. And so the mystery remained. As physics advanced into the 20th century, the question became even stranger, because scientists began discovering that space and time are not separate things. They are part of a unified structure, a structure now known as spacetime. And this realization would completely transform our understanding of dimensions. For thousands of years, space and time were treated as completely separate things. Space was the stage. Time was the clock. Events happened somewhere in space and at some moment in time. Simple. Intuitive. Wrong.
In 1905, Albert Einstein introduced a revolutionary idea that would permanently alter our understanding of reality. Space and time are not independent entities. They are woven together into a single 4-dimensional structure called spacetime. At first, this sounds like a mere technical detail, but it changes everything. Imagine watching a distant galaxy through a telescope. The light reaching your eyes today may have left that galaxy millions or even billions of years ago. You are not seeing the galaxy as it is. You are seeing it as it was. Looking farther into space means looking farther into time. Distance and time become inseparable. The universe is not merely spread across space. It is stretched across space-time. In Einstein's picture, every object traces a path through this 4-dimensional arena. Even when you are sitting completely still, you are moving through time. Every second, your existence advances along a trajectory through space-time. This concept became even more powerful in 1915 when Einstein completed his general theory of relativity. Before Einstein, gravity was viewed as a force pulling objects together. Newton imagined an invisible attraction acting across empty space. General relativity replaced that picture entirely. Gravity is not a force. Gravity is geometry. Mass and energy tell spacetime how to curve. Curved spacetime tells matter how to move.
This statement sounds abstract until you visualize it. Imagine placing a heavy bowling ball on a stretched rubber sheet. The sheet bends downward. Now roll a smaller ball nearby. The smaller ball follows the curved surface. It appears to be attracted toward the bowling ball. Not because an invisible force pulls it, because the geometry guides its motion. Einstein realized that planets orbit stars for a similar reason. Earth is not being pulled around the sun by an invisible rope. Earth is following the natural geometry created by the sun's enormous mass. In reality, the mathematics is far more sophisticated than the rubber sheet analogy. The analogy only curves space in 2 dimensions. Einstein's equations describe curvature throughout 4-dimensional spacetime. Nevertheless, the central insight remains astonishing. What we call gravity may simply be the shape of dimensions themselves. This idea was tested repeatedly. Every test succeeded. The orbit of Mercury, the bending of starlight, time dilation, gravitational redshift, black holes, gravitational waves. Again and again, nature confirmed Einstein's vision.
The dimensions of space-time are not passive containers. They actively participate in physical reality. And this creates a new mystery. If gravity emerges from geometry, why does that geometry possess exactly 3 spatial dimensions? Einstein's equations themselves do not strictly require 3 dimensions. Mathematicians have successfully generalized general relativity to other numbers of dimensions. The equations still work. The geometry remains consistent. Yet our universe chose 3. The question survives. In fact, it becomes even more important, because now dimensionality influences the structure of spacetime itself. To appreciate the consequences, we need to leave Earth and travel outward into the cosmos. The largest structures in the observable universe reveal just how deeply 3-dimensional space shapes reality. Galaxies are among the most magnificent objects known to science. Each galaxy contains enormous collections of stars, gas, dust, dark matter, magnetic fields, planets, black holes, and radiation. Our own Milky Way contains roughly 100 billion stars. Some estimates suggest even more. And the observable universe may contain hundreds of billions, perhaps trillions of galaxies. Yet these cosmic islands do not form randomly. Their structure emerges from gravity operating within 3-dimensional space. Shortly after the Big Bang, the universe was remarkably smooth. Tiny fluctuations in density existed, small regions slightly denser than their surroundings. Over billions of years, gravity amplified those fluctuations. Dense regions attracted additional matter. Matter attracted more matter. Small clumps grew larger. Eventually, stars formed, then galaxies, then clusters of galaxies, then enormous filaments stretching across hundreds of millions of light years. The resulting structure is known as the cosmic web. One of the most extraordinary discoveries in modern cosmology is that the universe resembles a vast network. Galaxies gather along gigantic filaments. Between them lie enormous voids, regions almost empty of matter. When astronomers map millions of galaxies, the universe appears less like a random scatter and more like a colossal 3-dimensional spiderweb extending across cosmic distances.
This pattern emerges because gravity spreads through 3-dimensional space. Change the dimensionality, and the growth of cosmic structure changes dramatically. Computer simulations show that galaxy formation depends sensitively on how gravity behaves. Even small alterations to dimensionality produce radically different universes. The galaxies we see today may be direct consequences of living in a 3-dimensional cosmos. And galaxies themselves reveal another clue. At their centers often reside supermassive black holes. Some contain millions of solar masses. Others contain billions. These objects push space-time to its limits. Near a black hole, Einstein's geometric picture becomes extreme. The curvature grows immense. Time slows. Light bends. Space itself becomes distorted. Black holes provide laboratories for exploring dimensions because their properties depend strongly on dimensionality. In 3-dimensional space, black holes possess specific characteristics predicted by general relativity.
Their event horizons have precise mathematical forms. Their stability depends on the geometry of spacetime. When physicists extend black hole mathematics into higher dimensions, entirely new behaviors emerge. Some higher dimensional black holes become unstable. Others can form shapes impossible in our universe. Instead of simple spherical horizons, they may resemble rings or more exotic structures. These solutions arise naturally in higher dimensional gravity. The mathematics suggests that dimensionality profoundly influences what kinds of objects can exist. This raises a provocative possibility. Perhaps 3 dimensions are not arbitrary. Perhaps they are selected because they allow stable structures to emerge across many scales. Atoms, stars, galaxies, even black holes. As physicists explored these questions, another remarkable connection appeared. The very equations governing waves and information seem unusually compatible with 3-dimensional reality. Consider light. Every star in the night sky sends electromagnetic waves across enormous distances. These waves obey Maxwell's equations, formulated during the 19th century by James Clerk Maxwell. Maxwell united electricity, magnetism, and light into a single framework. His equations predicted electromagnetic waves before they were directly observed. They remain among the most successful equations ever discovered. Yet Maxwell's equations also depend on geometry. The way electric and magnetic fields spread through space reflects the dimensional structure of the universe.
Three-dimensional geometry is built directly into the mathematics. The same is true for many other physical laws: quantum fields, fluid dynamics, acoustics, thermodynamics. Everywhere physicists look, dimensionality appears deeply woven into the fabric of explanation. But perhaps the most profound connection emerges from quantum mechanics. Quantum theory governs atoms, molecules, particles, radiation, and ultimately every known material object. It is extraordinarily successful. No scientific theory has ever produced more precise predictions. Yet quantum mechanics introduces a shocking idea. At fundamental scales, particles are not tiny billiard balls. They are quantum objects described by probability waves. Before measurement, nature does not always possess definite outcomes. Instead, reality evolves according to mathematical possibilities. Electrons behave this way. Photons behave this way. Even entire atoms can behave this way. The quantum world is strange beyond ordinary intuition.
And dimensionality influences it in unexpected ways. The allowed quantum states of atoms depend critically on the geometry surrounding them. The existence of stable atomic orbitals is connected to the dimensional structure of space. In universes with significantly different dimensionality, atoms may not possess stable configurations. Without stable atoms, chemistry disappears. Without chemistry, biological complexity disappears. Without complexity, observers disappear. Again and again, three dimensions seem unusually fertile. Not uniquely proven, but remarkably favorable. This observation became increasingly difficult to ignore during the 20th century. Every major layer of reality appeared linked to dimensionality. Gravity, atomic physics, stellar evolution, galaxy formation, quantum mechanics, information flow. The deeper scientists investigated, the more dimensions seemed fundamental rather than accidental. Yet, a problem remained. Physics had become incredibly successful at describing how dimensions behave. But nobody knew why dimensions exist in the first place. Where did space come from? Why should reality possess dimensions at all? And if dimensions are fundamental, why exactly three? To answer that question, physicists began pushing beyond Einstein, beyond quantum mechanics, beyond everything previously known. And there they encountered one of the most surprising possibilities ever proposed. What if space actually has more dimensions than we can see? What if three-dimensional reality is only part of a much larger structure, hidden beyond ordinary perception? The idea sounds like science fiction, yet some of the most serious theories in modern physics suggest precisely that. And those hidden dimensions may hold clues to why our visible universe appears the way it does. When physicists first began seriously questioning whether space might contain hidden dimensions, it was not driven by imagination or philosophy. It came from equations. In the 1920s, Theodore Kaluza and Oscar Klein explored a radical idea. They asked a simple question. What happens if Einstein's gravity is written not in 4 dimensions of spacetime, but in 5? At first, nothing seemed special about adding an extra dimension mathematically. You can extend the geometry, you can write new equations. Everything still works. But then something remarkable happens. When the equations are carefully examined, the extra dimension does not remain meaningless.
it begins to behave like electromagnetism.
In other words, gravity in 5 dimensions naturally contains both gravity and light in 4 dimensions. This was one of the earliest attempts to unify forces through geometry. A shocking suggestion emerged. What if different forces are not separate things at all? What if they are simply different expressions of higher dimensional geometry? Kaluza-Klein theory did not fully succeed as a complete theory of nature, but it introduced a powerful idea that would echo through decades of physics. Hidden dimensions might not be optional. They might be essential. But if extra dimensions exist, why don't we see them? Why does reality feel strictly 3-dimensional? Klein proposed an answer that still shapes modern thinking. The extra dimension might be curled up, not extended like the familiar directions of space, but compact, tiny, and tightly wrapped at scales far smaller than atoms. Imagine a garden hose seen from far away. From a distance, it looks like a 1-dimensional line. But up close, you see it has a circular dimension wrapped around it, a tiny second direction hidden from macroscopic view. Klein suggested that space itself might behave like that hose.
Large dimensions are extended. Extra dimensions are curled into extremely small shapes, so small that no experiment has yet been able to directly detect them. This idea opened a new frontier in physics. If extra dimensions exist but are compactified, then the structure of space is far richer than everyday experience suggests. And it also raises a deeper question. Why would nature choose to hide dimensions instead of simply removing them? As physics moved into the later 20th century, this question became even more urgent, because new theories began to demand extra dimensions rather than merely allow them. One of the most influential frameworks to emerge is string theory. In string theory, the fundamental building blocks of reality are not point-like particles. Instead, they are tiny vibrating strings. Each vibration corresponds to a different particle. One vibration produces an electron. Another produces a photon. Another produces a quark. Everything becomes different notes of a cosmic instrument. But here is the critical point. For the mathematics of string theory to remain consistent, spacetime must have more than 4 dimensions. In many versions, 10 dimensions are required. In some, 11.
The extra dimensions are not optional. They are necessary for the equations to avoid contradictions. This is one of the most surprising outcomes in modern theoretical physics. A theory designed to unify everything demands a universe with hidden geometric structure. But again, we do not observe these extra dimensions directly. So they must be compactified, similar to Kaluza-Klein's idea, but in far more complex geometries. These hidden shapes are not simple circles. They can be intricate mathematical structures known as Calabi-Yau manifolds. Their geometry determines how particles behave, what masses they have, and even what forces exist in the lower dimensional universe we observe. In a profound sense, if string theory is correct, then the properties of our universe are shaped by the geometry of unseen dimensions. This leads to a striking idea. The universe may not just contain laws. The laws themselves may emerge from geometry. At this point, the question of why 3 dimensions transforms again. It is no longer only about gravity or planets or atoms. It becomes a question of why only 3 dimensions are large and observable, while others remain hidden. One possible explanation comes from stability. In many theoretical models, only 3 spatial dimensions allow long-term stable expansion of large-scale structures while still permitting compact hidden dimensions. Another idea comes from cosmology itself. In the very early universe, all dimensions may have existed at similar scales. But during cosmic evolution, some dimensions expanded while others remained small. Why this symmetry breaking occurred is still unknown. However, some models suggest it could be related to energy minimization, vacuum stability, or quantum fluctuations in the earliest moments after the Big Bang. To understand this, we must travel back to the beginning of everything. Not just the formation of galaxies, but the origin of spacetime itself. According to modern cosmology, the universe began in an extremely hot, dense state. But what is less often explained is that space itself was dynamic. Dimensions were not fixed. They could, in principle, evolve. In some speculative models inspired by quantum gravity, the early universe may have had all spatial dimensions tightly coupled at microscopic scales. As the universe cooled, a phase transition could have occurred, much like water freezing into ice, but happening to the structure of space itself. Certain dimensions expanded and became large. Others remained compact. This idea is still theoretical, but it provides a possible dynamical reason for why we observe exactly 3 large dimensions. Yet even this does not fully settle the issue.
Because we still do not know why the transition favored 3. Why not 2? Why not 4? To move deeper, physicists turn to something even more fundamental than geometry: entropy and information. In modern physics, the universe is not just matter and energy. It is also information. Every physical state can be described in terms of information content, and the flow of time may be closely tied to how information is distributed. In this framework, dimensionality affects how information spreads. In fewer dimensions, information spreads too slowly or becomes constrained in ways that limit complexity. In higher dimensions, information disperses too rapidly, preventing stable structures from forming. But in 3 dimensions, something unusual happens. Information spreads in a balanced way, neither too restricted nor too chaotic. This balance may be one reason complex structures emerge so naturally in 3-dimensional space. Stars can form, but they remain stable. Galaxies can grow, but they do not dissolve instantly. Atoms can bind, but they do not collapse immediately. Complexity becomes possible, and complexity is essential for observers. There is another layer to this story, emerging from black hole physics. When physicists studied black holes deeply, they discovered something unexpected. The information content of a black hole does not scale with its volume. It scales with its surface area. This is known as the holographic principle. It suggests that the information in a region of space may be encoded on its boundary. This idea has profound implications. It hints that space-time itself may not be fundamental. Instead, it may emerge from deeper informational structures. If true, then dimensions may not be basic properties of reality. They may be emergent features of something more fundamental. This brings us closer to modern approaches to quantum gravity. Attempts like loop quantum gravity, holography, and ADS-CFT correspondence all suggest that space-time might arise from more primitive mathematical relationships. In some of these frameworks, geometry is not the starting point. It is the result. And if geometry is emergent, then dimensionality is also emergent. This leads to one of the most radical possibilities in all of physics. Space may not have always existed in its current form. It may have grown dimensional structure from deeper quantum rules. At this stage, the question, why does space have 3 dimensions, may not even be fully well posed, because the answer might depend on how space-time itself emerges. But despite all these theories, no final explanation exists. No experiment has confirmed extra dimensions.
No measurement has revealed hidden geometric directions. No theory has definitively derived why 3 dimensions are special from first principles. So physics remains in a strange position. We have extremely powerful mathematical frameworks. We can describe what happens in 3-dimensional space with extraordinary precision. We can even imagine universes with different numbers of dimensions and study their consequences.
But we still do not know why reality chose this particular configuration. And as we push deeper into quantum gravity, black hole thermodynamics, and early universe cosmology, the mystery only grows sharper. Because every layer we uncover seems to point toward the same conclusion. 3 dimensions are not just where we live. They are deeply woven into every successful description of the universe we have ever built. And yet, beneath all of it, the reason remains hidden. Still waiting, still unresolved, and possibly connected to something even deeper than space itself. To understand how deep this mystery truly goes, we have to shrink our perspective farther than any microscope can see. Farther than atoms, farther than protons, farther than quarks, farther even than anything directly observed. Eventually, we arrive at a scale known as the Planck length, about 1.6 times 10 to the negative 35 meters. This number is so unimaginably small that if an atom were enlarged to the size of the observable universe, the Planck length would still be microscopic by comparison. Physicists believe this scale marks a fundamental boundary. Beyond it, our current understanding of space and time breaks down. The smooth spacetime described by Einstein can no longer be trusted. The reason is simple. General relativity and quantum mechanics are both enormously successful.
Yet, when pushed to extreme conditions, they become incompatible. Einstein's theory treats space-time as smooth and continuous. Quantum theory tells us that nature is fundamentally fluctuating and uncertain. At ordinary scales, the two descriptions coexist peacefully. At the Planck scale, they collide. And nobody yet knows exactly what emerges from that collision. One possibility is that space-time itself becomes turbulent. Instead of a smooth geometric fabric, reality may resemble a seething ocean of microscopic fluctuations. This concept is sometimes called quantum foam. The term was introduced by physicist John Wheeler. According to this picture, space-time at incredibly small scales is anything but smooth. Tiny fluctuations constantly appear and disappear. The geometry itself fluctuates. Distances become uncertain. Even the structure of dimensions may fluctuate. At these scales, asking whether space has exactly 3 dimensions may become surprisingly complicated, because dimensionality itself may no longer be fixed. Some approaches to quantum gravity suggest that the effective number of dimensions changes with scale. At large scales, space behaves as 3-dimensional. At extremely small scales, the dimensionality may decrease. Several independent quantum gravity models have hinted at this possibility.
In certain calculations, space-time begins acting as though it possesses fewer dimensions near the Planck scale. This is one of the most intriguing developments in modern theoretical physics. The universe may not have a single dimensionality. Dimensionality itself could emerge differently depending on how closely reality is examined. Imagine looking at a coastline from space. From orbit, it appears smooth. As you move closer, complexity emerges. Closer still, new structures appear. The measured length changes depending on scale. The geometry reveals hidden layers. Some physicists suspect space-time may behave similarly. 3-dimensional space could be a large-scale phenomenon emerging from deeper microscopic structures. If this is true, then the familiar dimensions around us are not the foundation of reality.
They are the result of something more fundamental. But what could be more fundamental than space itself? For centuries, such a question would have sounded absurd.
Today, it sits at the frontier of theoretical physics. One candidate involves networks of quantum information. In several modern approaches, relationships between quantum states appear capable of generating geometric properties. Distance may emerge from information. Geometry may emerge from entanglement. Space itself may emerge from connectivity. The implications are astonishing. What we perceive as physical separation might not be fundamental. The dimensions surrounding us could arise from deeper informational relationships hidden beneath spacetime. Some researchers compare this to a computer screen. The images appear real and continuous. Mountains, rivers, cities. Yet underneath lies a completely different level of organization. Pixels, electronic states, information processing. The visible world emerges from something deeper. Likewise, three-dimensional space may emerge from structures that do not themselves possess familiar dimensions.
This possibility becomes especially fascinating when considering the observable universe as a whole. Today, the observable universe spans roughly 93 billion light-years in diameter. It contains hundreds of billions of galaxies. Each galaxy contains billions of stars. Around many of those stars orbit planets. On at least one planet, chemistry became biology. Biology became intelligence. And intelligence became capable of questioning the dimensions of reality itself. This chain of events is extraordinary because every stage depended upon the stability provided by three-dimensional space. Stars formed because gravity operated in a specific way. Stars survived because nuclear fusion remained stable. Heavy elements formed because stellar interiors behaved predictably. Planets emerged from rotating disks of matter. Chemistry developed through stable atomic structures. Life evolved through molecular complexity. Every link in the chain traces back, directly or indirectly, to the dimensional structure of the universe. If dimensions had been different, the cosmic story might have ended before it began. No galaxies, no stars, no planets, no observers, no questions. This realization gives the mystery a special character. Many scientific questions concern specific objects. Why does a planet have rings? Why does a star explode? Why does a black hole form? The question of dimensionality is different. It concerns the stage upon which every physical process unfolds. It asks why reality possesses the framework necessary for all other explanations. And despite centuries of scientific progress, we still do not know.
Perhaps future experiments will discover hidden dimensions. Perhaps a successful theory of quantum gravity will derive three dimensions from deeper principles. Perhaps cosmology will reveal why only three dimensions expanded after the birth of the universe. Or perhaps the answer lies in a direction nobody has yet imagined. History provides reason for humility. Many mysteries once seemed impossible. The motion of planets, the nature of light,
The origin of stars, the age of the universe, each eventually yielded to human curiosity. Yet each answer also revealed deeper questions waiting underneath. The mystery of dimensions may be one of those questions, a doorway leading beyond our current understanding. And what makes it especially fascinating is that it hides in plain sight. Every object around you occupies three-dimensional space. Every step you take depends on it. Every star you see in the night sky shines within it. Yet, because it is so familiar, we rarely stop to ask why it exists at all. the universe could have been radically different. Mathematics allows it. Physics can imagine it. Yet reality chose this particular arrangement. 3 large dimensions, 1 dimension of time. A cosmos capable of forming galaxies, stars, planets, and minds. A cosmos capable of wondering about itself. When we look at the great spiral galaxies turning slowly in the darkness, when we observe black holes bending spacetime, when we trace the cosmic web stretching across billions of light years, we are witnessing the consequences of a geometric choice made at the deepest level of reality. A choice whose origin remains unknown. Perhaps someday a future physicist will uncover the final explanation. Perhaps hidden dimensions will be detected. Perhaps space-time will be shown to emerge from quantum information. Perhaps the ultimate theory of nature will reveal why reality could never have been any other way. Until then, the question remains open, one of the oldest and deepest mysteries in science. Not merely why galaxies exist, not merely why stars shine, but why the arena in which everything exists possesses the shape that it does. And so, after traveling from Newton's gravity to Einstein's spacetime, from atoms to galaxies, from black holes to quantum foam, from hidden dimensions to the edge of modern physics, we arrive back at the same deceptively simple question. A question hidden beneath every object, every force, every law of nature. Why does space have 3 dimensions? For now, the universe remains silent. And perhaps that silence is what makes the mystery so beautiful. Because somewhere beyond our current knowledge, beyond the limits of today's theories, beyond the horizon of what humanity presently understands, an answer may still be waiting to be discovered.